All right, so now we were at the point where we were at step 6, and we had just balanced the half reactions by multiplying the first reaction by 6 in order for the electrons to balance, to be able to cancel out. Okay, and so step 7 was to just basically rewrite the reaction together instead of in half reactions, writing them all together. And so after you do that, then you're going to want to reduce any redundant species. Okay, so the only thing here that we can reduce that's common on both sides are the 6 electrons here. Iron's different here, that chromate. So everything is different except for the 6 electrons. They're the common ones, so we can cancel those out. All right, so now we need to be able to balance the charges. Okay, so it shows you that here. And so what we need to do is basically we're going to take the coefficient and multiply it by whatever the overall charge is on the atom or the compound. And so here 6 times plus 2, so 6 times plus 2, so that's plus 12. Okay. Then here the coefficient's nothing there, so it's assumed to be 1. So plus 1 times negative 2, which is a negative 2 there, plus 14 times 1, positive 1, so that's 14, right? So here we have to add up our charges. So when you see the arrow, that should be the equal sign, right? So the number of charges here should be the same as that on the other side. So here we have 12 minus 2, so that's 10. 10 plus 14, and that's 24. All right, so that's how many charges we have on one side. Now we need to make sure the charges are the same on the other side. So 6 times positive 3, 6 times positive 3, so that's a positive 18. 2 times positive 3, so plus 2 times positive 3, that's positive 6. Plus 7 times, this is a neutral atom, so that's, or compound, so that's 0, right? This is all completely neutral. So 7 times 0 is 0, all right, so plus 0. So 18 and 6 is also 24, all right? So 24 is equal to 24, and so now we have a balanced redox reaction where the actual charges are also balanced. So before, when we were balancing chemical equations, we were just balancing the type of atoms. You know, if you had 6 irons on this side, you had to have 6 irons on the other side. But with redox reactions, we have to balance, like we did before, you know, making sure the number of element types are the same on both sides. But we also have to balance the charges. We have to balance the electrons. Okay, so that process involves a lot more steps than just simply balancing a chemical reaction. Okay, so there are some problems in our textbook that I would like to look at regarding redox reactions. Okay, so if we go and take a look at that, let's see here. Example 4.6 here, we have a redox reaction where they're asking us to classify the type of redox reaction it is by providing a name, and for those reactions that are redox, name the oxidant and the reductant. Okay, so for this problem here, we're having to figure out whether the reaction is a redox reaction or not. And so in order to figure that out, we have to figure out the oxidation numbers on 2 different elements. So here we have a common element here is zinc. Okay, and then here we have carbon as well, and then oxygen. Okay, so here we have zinc in a compound. This is a neutral compound. It has to add up to 0. Oxygen is going to be -2. So Sometimes when you have something like this where you have a transition metal and you have carbon, you don't really know what it's going to be. You remember that carbonate has a -2 charge. So you have to kind of break this part apart first, figure out carbon, and then you can figure out zinc afterwards. So here, oxygen is -2, so -2 times 3 is -6. So carbon has to be +4 in this case. Okay, so +4. So here we have, overall, we have oxygen being 3 times -2, which is -6. 1 times +4, which is +4. So that means zinc must be +2. And zinc is actually one of those elements where it's always +2. It's one of those odd ones. And so if you remember on your in your textbook, there is a periodic table and it shows you the elements that are consistent, and zinc is one of those that always has an oxidation number of +2. All right, so here zinc is also +2 because it's always +2, and oxygen is -2. All right, so they cancel out. But notice zinc did not change. From +2 to +2 did not change. Oxygen went from -2 to -2 here, did not change. Even with carbon dioxide, here oxygen is going to be -2, it's -4, so carbon is +4. Again, carbon being +4 on both sides, both times. All right, so we do not have a redox reaction here. So not a redox reaction because the oxidation numbers did not change. Okay, so there's no oxidation reduction going on here. For number 2, we have to assign oxidation numbers again. Gallium here is going is uncombined, so its oxidation number is 0. Bromine's also, its oxidation number is 0, it's uncombined. Here, this is a neutral compound, it has to add up to 0. Bromine's going to be -1. I know there's not a rule for it, but like I said, halogens usually, if you can't figure it out, it's going to be a -1, group 17. All right, so 3 times -1 is -3. So gallium must be +3 in this example here. All right, so gallium went from 0 to a +3, and then bromine went from 0 to a -1. All right, so gallium became oxidized, bromine became reduced. Okay, so if something becomes oxidized, you refer to that as the reducing agent because it's reducing the other species. And if it's reduced itself, it is the oxidizing agent. Okay, because it's relevant to the other guy, not the individual itself. So when bromine became reduced, it became the oxidizing agent. When gallium became oxidized, it became the reducing agent. All right. Next example here, we have the breakdown of hydrogen peroxide. So here we have hydrogen should be +1, so +1 times 2 is +2. Oxygen is -2 times 2, which is -4. But here we have a peroxide, so it's not -2, it's -1. So -1 times times 2, which is -2, and it adds up to 0. All right, so here with water, it has to add up to 0 too. It's a neutral compound. Oxygen is -2, hydrogen is +1. These are all rules here. So 2 times 1 is +2. So +2 plus a -2, that adds up to 0. So hydrogen went from +1 overall, or not overall, but individually to +1. So hydrogen didn't change in this example. Oxygen here went from -2, -1 to -2, so it did change. So oxygen went from -1 to -2. And then this oxygen here went to 0. So then you have another case where oxygen went from -1 to 0. Okay, and this is referred to, so we have one element that is being both, here it's being reduced, and here this is being oxidized. So this is referred to as a disproportionation reaction, okay, where you have one element that's undergoing both oxidation and reduction because it's basically splitting up into two different molecules or compounds, okay, and you're able to see the redox numbers change. So the oxidation numbers are different in each case. All right, so if this guy is being reduced, this would be, referred to as the oxidizing agent. If this one's being oxidized, it's being referred to as the reducing agent. All right. So for part D here, I'm going to again assign the oxidation numbers for every element here. So here I have barium is +2. Okay, there's one of those, so it's +2. And then chlorine's -1 times 2, which is -2. Okay, potassium's group 1, so it's +1, so it's +2 overall. Oxygen's -2 times 4, which is -8. So the sulfur there must be +6. Okay. And then for barium's +2 because it's group 2. Oxygen's -2 times 4, which is -8 overall. That's it to 0. Sulfur in this case must be +6 again. Okay. So notice potassium here, and potassium is always going to be +1. That's the rule. Okay. And then chlorine's -1 here, it's -1 there. Sulfur is +8 here, +6 here, and it's +6 there. Oxygen's -2 in both cases there. So you don't see a change in the redox in the oxidation numbers. So there's really no redox reaction going on. So that's what you would classify it as. You just write not a redox reaction. And that's because the oxidation numbers do not change. All right, so see if I can focus that better. Okay. All right, so here again, same strategy. We're trying to figure out if this is an oxidation redox reaction or not, whether oxidation or reduction is occurring. So here I'm going to assign oxidation numbers again. They have to add up to 0. It's a neutral compound. Here with carbon, we don't have a rule here. For hydrogen, we do. It's going to be +1. So 4 times +1 is +4. And then this has to be -4 overall. So 2 times, it has to be +2, which would be, actually, since hydrogen's there, it's going to have to be -2. So it's going to have to be -4 there. All right, so here oxygen, we have it by itself, so it's 0. And then here oxygen is -2, and so it has to add up to 0. It's a neutral compound. -2 times 2 is -4. Carbon must be +4 there. Okay, and then we have water here adds up to 0. We have -2 for oxygen, and then we have +2 for hydrogen, because each hydrogen atom is +1, oxygen is -2. All right, so here we see, let me look at this again. All right, so here we see a change in the redox or the oxidation numbers of for carbon. All right, so hydrogen is +1 in both cases. Oxygen's -2 in both cases. Carbon, though, went from -2 to +4. And then here we see oxygen actually go from 0 to -2 there. All right. So it went from, it didn't change here to here, but it changed from -2 here to 0 there. So for carbon, it went from a -2 to a +4. And then for oxygen, in this case here, it went from 0 to -2. All right, so here we see carbon is being reduced or oxidized, and then oxygen is being reduced. Okay, so our carbon is going to be our reducing agent, because that's what it's doing to the other guy. And if it's being reduced, it's our oxidizing agent. So this is a redox reaction where we see a difference in the oxidation numbers. All right, so I wanted to go ahead and move on to stoichiometry, and then we're going to come back and do another problem where we're balancing a redox reaction. So what is stoichiometry? So stoichiometry is basically a way to mathematically determine the amount of reactants you need in order to produce a certain amount of products. And you'll find with the math you can actually go different ways. So for example, if you instead of wanting a certain product, you can start with a certain amount of reactants. And so for example, like in the lab, sometimes you only have a certain mass of a reactant that you have, and so in that case you could figure out how much product you could make. Or if you had an idea of a certain amount of product you could make, then you would use some math to calculate the amount of reactants you needed. Stoichiometry is very useful, and that's why you see it at high school level, you see it at the college level. You do it, the calculations all the time in the lab. And so it's one of those basic skills you're going to need. Even if you're in biology or a different area of science, when you're having to do experiments and they involve chemicals, you're going to have to make up solutions. And a lot of times you're also going to have to consider stoichiometry in the process. And so in order to understand stoichiometry, we need to sort of start with the basics. So with the stoichiometry, you have to start out with a balanced chemical equation. Okay, and that's exactly why we learned how to balance chemical equations, because we're going to be reliant on the coefficients in those chemical equations. And of course, when you balance chemical equations, those coefficients can change, and they should, in order to reflect, that there is no atoms being lost or gained, right? No matter is lost or gained during a chemical reaction. So chemical formulas provide the identities of the reactants and products involved in a chemical change. The coefficients provide the relative numbers of these chemical species. The quantitative relationships between the amounts of reactants and products are known as a reaction stoichiometry. And so the coefficients are what are telling us how much we have in what's referred to as the molar ratio. We'll learn about that a little bit later, but that involves the coefficients. So here's an example that you are probably familiar with if you've ever had to use a recipe to cook something. Here we're trying to cook pancakes. Okay, so we have a recipe for pancakes. To make 8 pancakes, the recipe calls for a cup of pancake mix, 3/4 of a cup of milk, and 1 egg. And so if you wanted to write the recipe as a chemical equation, your reactants would be 1 cup of mix of the pancake mix, 3/4 of a cup of milk, and 1 egg. And then your products would be 8 pancakes. That's what you're going to make at the end, and hopefully they'll be nice and fluffy and not burnt. So here, if we're wanting to use this example mathematically and calculate, for example, how many eggs it would take to make 24 pancakes. So here we have this, our general equation here, our recipe equation. If we need to make 2 dozen pancakes, so 2 dozen is 24. The amount of ingredients needed may be increased proportionally according to the amounts given in the recipe. So here we have 24 pancakes, and my molar ratio here, refer to this as molar ratio. This is not going to be, maybe it should be called my egg ratio. So my egg ratio is I need 1 egg per 8 pancakes. So how did I get that? So I'm using the coefficients here. 1 egg will make 8 pancakes. So I'm setting it up as an equivalent because they are. So we can set up 1 egg is equal to 8 pancakes, 8 pancakes over 3/4 cup of milk. So we can set this as basically a conversion factor. 1 cup of mix can equal to 1 egg, etc. These are equivalents basically in this chemical equation. Okay, so when our units cancel out for pancakes, we're left with eggs, and we can figure out how many eggs we need to make 24 pancakes. All right, balanced chemical equations are used in a similar fashion as recipes. So from a balanced chemical equation, we can determine the amount of one reactant required to react with a given amount of another reactant, the amount of reactant needed to yield amount of product. All right, so we can figure out all these things because everything in the chemical reaction is equivalent, so we can make different types of molar ratios. All right, so here we have an egg ratio. How many eggs per pancake? Okay, but we can look out to see how many eggs. Look at the egg to milk ratio, or the egg to cup of mix ratio, or etc. So the possibilities are there's definitely more than one possibility in this situation. All right, so the coefficient of the balanced equation are used to derive stoichiometric factors that permit computation of the desired quantity. So starting out with a balanced chemical equation is key. Okay, so sometimes they will sort of hint to you that you need to actually balance it before you get started. So just keep that in mind, that the equation may not be balanced when you're starting off, and they expect you to balance it. All right, so here we see that this reaction is in fact balanced. It says this equation shows that ammonia molecules are produced from hydrogen molecules in a 2:3 ratio. All right, so stoichiometric factors may be derived using any amount or number unit. All right, so here, like I was saying earlier, you see the different types of molar ratios you can use. So 2 ammonia molecules, for example, is equal to 3 hydrogen molecules. All right, so these are conversion factors. These is called the molar ratio. So basically it takes, well, you can talk about it in 2 different ways. 2 molecules of ammonia is produced for every 3 hydrogen molecules, all right? Just like 2 dozen ammonia molecules is equal to 3 dozen hydrogen molecules. All right, so what the point they're trying to make here, or technically it's not right, but in a chemical equation, the coefficient basically represents either the number of molecules or the number of moles, and so that's what they're trying to show here. So for every 2 moles of ammonia produced, I need 3 moles of H2 gas, and I also need 1 mole of N2 gas. All right, you need both of these things. But these are our molar ratios we're able to set up from the balanced chemical equation. Okay, and so you can, these coefficients do represent number of molecules. Okay, they do represent the number of moles. All right, so when we're talking about stoichiometry, we're really focused on moles and not so much molecules. But you can express this chemical equation in words. We're referring to that the unit for the coefficient there as molecules as well. All right, so here's our first example. how many moles of I2 are required to react with 0.429 moles of aluminum according to the following equation. So here we're going to have to move on to our textbook. Okay, so here we have our balanced reaction. 2 moles of aluminum react with 3 moles of iodine to yield 2 moles of aluminum iodide. Okay, so here it's asking how many moles of I2, so moles of I2, are needed to react with 0.429 moles of aluminum. So 0.429 moles of aluminum. Okay, so this reaction is, well, we're only going to have to use one conversion factor in this case, which is called the molar ratio. All right, so our molar ratio here, it depends on what we have and what we need. All right, so first I'm going to write my given information over 1. So this is sort of, we're approaching this just like we did with any conversions, because this is pretty much what it is. It's just a conversion problem. All right, so we have 0.429 moles of aluminum. All right, so now I need to figure out my molar ratio. So how many moles of aluminum do I need to react with how many moles of iodine? So I can write my molar ratio between these two species as 2 moles of aluminum over 3 moles of I2. Notice I'm using the coefficients and the units moles. Or I can write it the other way around, 3 moles of I2 over 2 moles of aluminum. So obviously, you only have one right answer here. So our units for moles of aluminum are on the top, so I need the same thing on the bottom. So I would use this version here. So 3 moles of I2, what I want on top, and what I have already on the bottom, so 2 moles of aluminum. So the units here are common, so they cancel out. Okay, and then I do the math. So 0.429 times 3, and that is 1.287 over 1 times 2, which is 2. So then I divide that, and I get 0.6435, and that's moles of I2. So here, if I'm starting out with 3 sig figs, so it's going to be 0.64 round the 3 to 4 moles of I2. Okay. All right, so that's how you do a simple one-step conversion. A mole, it's called a mole-to-mole problem. All right, we're converting moles of aluminum to moles of I2, okay, using what's called the molar ratio, okay? It's called the molar ratio. And that's when you're using your chemical equation and the coefficients there in terms of the units moles, okay? And so you're using your balanced chemical equation to figure out, be able to convert moles of aluminum to moles of I2. It basically tells you how much I2 you need, how many moles of I2 you need. And then you can go and calculate the mass of I2 that you need. And that would help you figure out, how much mass to use so that you can actually do the reaction. All right, so going back here we see a picture of aluminum and iodine reacting to produce aluminum iodide. So isn't that a very pretty reaction here? The heat of the reaction vaporizes some of the solid iodine as a purple vapor, and you can see that very nicely there. Okay, so here they're showing you that reaction, okay, and you get 0.644, which, we just did the calculation there. So here they're showing you a nice flow chart, okay, where this is example 4.9, another problem in your book. So we'll get to that just a minute. But this flow chart tonight, what I really would like to show you, honestly, is basically the relationship between moles and mass. And so this is sort of summarizing it in a nutshell, okay? But it might be better if you know what's ahead, because the problem that we just did is I refer to that as a one-step problem because it just involves one conversion factor, okay? But it's going to get hard enough to where you're going to have 3 conversion factors. That's as hard as it gets. You have 3 different conversion factors and you're converting grams to grams, for example. All right, so I'm going to go ahead and show you my flow chart that I like to show students. Actually, let me start here. All right, so say, for example, we have the mass of substance A. And I can go from mass of something to moles of substance A using the conversion factor molar mass. Okay, and then I can go from moles of A to moles of B using what I just used, which is called the molar ratio. Okay, so for example, in that previous example, I went from moles of aluminum to moles of iodide using my molar ratio. So that was just a simple one-step conversion. So notice here, if it involves an conversion factor, I write down the type of conversion factor. And then we go from moles of B to mass of B using, again, molar mass. So if you notice with stoichiometry, it may seem complicated, and it is. But if you look at it, there's just 2 different types of conversion factors you can use, that you have to use. Now, if you want to complicate this a little bit, you can go like that. And this is something we've already done. Convert moles to number of atoms or molecules. And that's our favorite conversion factor, Avogadro's number. Right? So you can always convert to atoms or molecules from moles. All right. So ignoring that part and just looking at this part here, we just did a simple mole-to-mole problem, okay? So you're going to encounter different types of problems. So a mole-to-mole problem is probably your easiest, mole of A to mole of B, okay? And then you can do a mole to mass, okay? Or the other way, it goes both ways, right? Or a mass to mass. Okay, so you can go moles to moles, mass to moles, moles to mass, mass to mass. So mass to mass is the harder problem where you have 3 different conversion factors that you have to use. All right, so we're going to build up to that. All right, so for Monday's lecture, we're going to start with talking about redox reactions, balancing redox reactions, and on Wednesday I'll probably end up doing one problem just because I want you guys to see it a couple of times because it's more complicated. It's one of the more complicated things we have to do, and so I want you guys to see enough examples to where you feel confident in that you're able to practice doing some problems and feel confident that you're able to balance redox reactions. All right, so we will continue stoichiometry on Monday for Monday's lecture.